that is what the ho-hum is. You just dramatize your topic, and then the next area is of course what exactly your aim. Aim sense, you're saying what the objective is, and then what are the steps that you're going to do, and so on. Then examples. The step 1, 2, 3, very broadly. So you're saying data analysis, if you know examples, maybe data analysis, real case examples, and you have data and so on. You present it in tables and so on and so forth, and then critical view, what can we do, and so on. And then 4, so what? In other words, you have proved everything that you started out with an objective, and so what? What is the next steps? What can we do? And then how do has my objective been met? So that's basically the broad line. So I would like to, in your write-up, maybe the objective, clearly case, write it what the objective are. This is going to be an experiment on blah blah whatever, and then how are we going to proceed? So in the laboratory experiment, you got to create the procedure, the sensors that you're going to use, and then maybe create some data or write a software. I don't know. If you find some sort of software to write, that'll be fine. So create data, it has been artificially created data. So, and then eventually at conclusion. So that's what I'm going to be expecting. So anyway, these are the broad 4 steps. You want to dramatize your problem, how it's so important, critical for the world to survive, and so on, and how we go about getting that. My object, clearly state. You don't have to go aim for the moon or the sun, but clearly state what are the objectives of my study here, and make it clear. So I'm expecting maybe more than 5 to 10 typed pages. And then I want makes a uniform format for all the papers. So what font you're going to use, size, and so on. And then maybe the paragraph higher for example, if you say objective, this may be 16 or something, the size will be, and then the text will be 12, I don't know, whatever, the font size. And then the you leave 1 space, 2 space, you decide it. But everybody has to follow the same format. I don't know whether you guys, when you submit or you look at any paper, they have some sort of a guidelines. If you can get a guideline from internet, that'll be fine. But I like all the 4 or 5 papers to follow the uniform format. That'll look nice. And then you create pictures, maybe necessary pictures. I don't want to create pictures just for the picture's sake, but pictures, tables. And if you have any software and so on, you can put that in appendices. You're deriving some formula, whatever, you can write it in the text, but you can put an appendix. You can derive it and put the tables in the appendix too, and pictures also, it doesn't matter. Or if it flows with the text, you can include in the text also. So whichever way, suit yourself, but it'll be nice. And then eventually each team, 1 member. I think hopefully everybody, all the 4 teams have got 3 members. Each one will contribute, and I would like to find out what each one contributed. And I don't want to surprise you. You can choose your spokesperson to present it. So everybody will listen to it, and one of the classes will make a presentation. Is there any questions? Anybody? ask a question? I heard some noise. I'm sorry, I am not in the screen with the Teams, so I don't know. Are there any questions on this? Or any comments, anything like that?
So do we need to make it like a full-fledged like a journal article with an abstract or anything, or just this?
I could not hear you properly. Can you be a little bit louder?
So I was asking if we need to make it like a full-fledged article with an abstract and introduction and everything, or will this do?
I don't think it's abstract is necessary. Just because I don't know if it is ready for submission, you can do that. Abstract, you send it in because they want to see whether you can accept it. Then you submit it. But this is just final submission. So write nicely, type it nicely with a objective, and you can put an abstract in the beginning if you want. That's okay. That's okay. If you want to summarize, what did you find in the first page? Summarize your summary of what your objective was, what did you find, and so on. That'll be good. So it'll be like a you know basically what they call executive summary. You know, an executive doesn't have time to really read through it, so he wants to look at the summary. Yeah, you can do it, no problem. And if you don't have it, that's fine too. So, but I think the important thing is I don't want to spend so much time, relatively good time, but distribute the job among yourselves. So what each one has to do. Maybe one guy is the per person to type it, perhaps, and everybody submits to that person. And eventually, I would like to get it. If you want to finish by middle of November, maybe second week I mean, after the first week, the beginning of the second week, I would like to get your draft so that at the end of that second week or beginning of the middle of the November, we can have the presentation. I think if the 5 people are to present with 15 minutes, so hour and a half is probably good enough. So if you want to choose a Saturday, your Saturday morning, that's fine with me. It's up to you. I'm not going to rob you of a Saturday, but if that was the best way to do it, I will be prepared. It'll be the Friday evening for me. I'll be fine. Is that everybody? Any comments on this? So the important thing is I want that do a thorough analysis, and make sure that you are being innovative. What exactly, what's the history about? For example, we have the solar heaters all over India, so you don't have to go through everything. What is the data on it? What do we have? How much capacity we have? That'll be useful. So something innovative. So I mean, the heaters, people have a number of books are available. You may want to just write one paragraph on it. But if you can collect data all over how they are using it, how is it saving it, and what exactly are the needs, and hopefully you can find material. I'm not trying to ask you to invent material. That'll be hard. But if you can get material, and there may be limitation, if it is limitations are there, present it in the text. We were limited by this, and so on. I'm not expecting to be full-fledged publishable paper or something like that. But don't underestimate yourself. I'm sure you can do it. So, and good luck to you guys. And there are, in the case of the Stefan Boltzmann, and we will go through that. Let me discuss that the 2 experiment that they are really making mistakes even in heat transfer laboratory. First is the conductivity experiment. So conductivity experiment, what they have is they have 3 materials, asbestos and one more plastic material, and all of them are non-conductors, insulators. So they have a heater here, and opposite to that, symmetrically, they're all cylinders. Okay, they're all cylinders plan wise. So they have the same 3 A, B, C, Hylon, I think, A, B, C, D, E, F, and they have thermocouples here, 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 okay, and here. So from the difference of the thermocouple, do you know how much heat is going? And then similarly here. And the mistake they did was they started assuming 50% is going here, 50% going here. If everything was working fine, but the asbestos was crumbling, So it was offering high thermal resistance. So not everything was going, one was wood and Hylam. So wood, Hylam, and asbestos. So what I did, okay, so they had measurement made and all these intersections. So there are 6 measurements or 8, I don't remember. So they were subtracting out, assuming 50%, they were getting even for wood 200% off. Those are experimental error. I mean, for 1 or 2 years, some of my previous heat transfer experiment in the experiment, they got the same thing, and I went and complained, oh, we're going to fix it. Then last year when I was there in the campus, I told them, bring me all the raw data. So what I did is, I assumed from the handbook, assume the conductivity of the wood, and assume the temperature, the conductivity, this is wood. So the principle being here is only one-dimensional heat transfer. That is the key. So you insulate all the sides, you drop it in some sort of insulation bath. So only the heat will only, the flux will only go one direction. So I knew the temperature of the wood, T1 and T2. So I calculated Q to be Ka multiplied by T1. T1 is higher than T2, or T2 is higher, or whichever. So I calculated the flux at both sides. So I knew, and one side was damaged, I knew exactly how much heat was going through everything. So using this Q on Q top and Q bottom, I calculate the K of Hylam and asbestos. And believe it or not, both sides agreed. Hylam on both sides were exactly same, even though the Q1 and Q2 were different. I used this the appropriate temperature difference, calculated K to be Q divided by area delta T. So for one material, 2 material, whatever. So I was able to do that with the arrangement. But so you need to describe, in IIT, I was visited IIT with my old professor at heat transfer at Sukatme. So he was doing another experiment, but that was the technique was a little bit different. There was some sort of a cylindrical thing, and then going radially, I think, the heat flux. So and you can also do this in a transient way too. In other words, you drop this in a transient bath, and depending upon how it is losing, you know the area and everything, use the transient methodology. Maybe you may want to describe 1 or 2 methodology. I don't know. It's up to you. So it's all up to your discretion. Okay. So on the heat transfer, radiation heat transfer, so they have a semi-hemisphere. So they have the shell here. They supply water, hot water on the shell. So they heat it up. It is all uniform temperature. So they have a sample coupon, and they paint it black. So it's black. So the radiation is coming in here. It's heating it up. So they make this steady state. So this is all temperature steady state here. Then from outside, they know the mass, Cp and everything, and they introduce this inside and then monitor the temperature in time. And from there they can set it. But I think they were making mistakes on it. I find this is one way. In other words, you find the temperature average, maybe 2-3 averages of the coupon. You know the mass of that, Cp, the conductivity, everything you know. So transient wise, it is changing. So from the transient, find out exactly what is the heat capacity. But obviously, every time it is also radiating heat out. So this is kind of a tough. You have to do it numerically. But anyway, I just want to. This is the technique they use in the lab, heat transfer lab in the campus. So this is going to reach some sort of steady state at that time, and from the steady state you cannot get T to the power of 4 because I don't know. Anyway, think about it. That's because this is losing heat depending upon its temperature. So at every temperature, at every time, you can substitute the how much is heating is being obtained from here, because you know that shape factor and everything, it's like a pi. But we will go through the theory a little later. But that's the technique they're using. You heat the conservation of energy equation, then maybe numerically integrate it to get the temperature, predicted temperature next time, and so on and so forth. But anyway, that is the technique that I would use, and find out, hopefully we can find some technique. And then green gas effect, I think you should really do some thorough analysis. That the inconvenience and truth. Well, I'll go. So he did, there was a video, I don't know if that's available on YouTube or anything, I don't know that. So it's a challenging subject, but it's very interesting, thought-provoking, very apt to the current condition. Some of the, even our US president doesn't believe in environmental effect, whereas the majority of the American people believe in it. So I think the whole world has to be aware of that. So we have to take steps right now, otherwise we won't exist as a community in this earth. So anyway, that's an interesting subject you've taken. Another two, the solar, again, the solar heater data and then solar generation of heat. I need to emphasize one thing, how the efficiency, apart from the alternative electricity generation, the efficiency of equipments is another important thing. I attended a seminar in Stanford many years ago. Can anybody enough you guess what is the power rating of your refrigerator? Can anybody tell me? I know when the power is spanned, when the compressor comes on. You guys are all very much interested in thermodynamics. Did you learn about refrigeration at all, Krishna? Anything about refrigeration?
Yes, we did.
You did, okay. So the majority power is, what is the average power of a typical refrigerator? Average power. The huge one, which is 20 cubic feet here, 2025. I don't know if that is a cubic liters. I'm not sure. I have to convert that. So let me tell you, before it's only 50 watts. Can you believe it or not? Just like a light bulb. The reason is, everywhere, every step of the way, there was legislation by California government. In other words, you cannot sell a refrigerator here unless your power rating is such. So over the years, it's very high, and maybe it was like 400 watts. I don't know. During maybe 1970s, it came down all the way. Everywhere legislation. Same way as automobile in the California. If I drive down to south to LA, by about 50 miles away, I could see brown on my horizon, completely small, about maybe 30 years ago. If you go now, nothing. So they legislated that every car has to be fitted with a catalytic converter. All the exhaust has to be captured by it. So every 2 years, I have to take my car for a smog test. And then same thing in India too. Right now they are instituting that. I don't know how effective they are, but they're very strict. So what I'm saying is, even in the generation of electricity, the government policy is a big aspect of it. I'm not saying that I think that's one of the aspects how you institute everywhere. Every state has to follow. Remember, even in Tamil Nadu, the capturing of your rainwater before you get building inspection, you need to have a facility to collect rainwater. I don't know. There was a principal, Shankaran, he's still the principal in Trichur. He has a house. He collects water from the rain. Believe it or not, his whole well fills up with 2 rains of Kerala. He doesn't need any more water from the city of Trishur for the rest of the year. Amazing. So anyway, what I'm saying is the government policy plays an important role in any of this alternative electricity generation, spending, and everything. So you may want to, I don't know whether you'll be, I'm just giving you for information's sake. So, okay. Any more questions on? Okay. Since I gave Krishna a paper on the history of the radiation history, how it developed into a real science. It was pre, let's see, okay, so let's see, I cannot do this one. Okay, let me just reduce it. Okay, so let me go through this. It's very interesting because remember, we were still at the rudimentary, starting of understanding the discrete form of energy and so on. So it's very interesting that it's since 1700 the scientists understood that heat is exchanged between 2 bodies. It's not linear. You remember, if Newton's law assumes a linear relationship between the cooling, Newton's law of cooling assumes, so until the low temperature transfer, they may be true, but as the temperature gets larger and larger, you find out there's a big discrepancy in doing that. There is some other mode should be there. So they developed a lot of theories to explain this high temperature phenomenon, why there is a discrepancy between the actual measurement and the theory that you're proposing, until an experimentalist, Joseph Stefan, he was a teacher at the University of Vienna. He was a good experimenter. He was not a theorist. So he found out that this is a unique problem. He was the first one to propose the temperature depends and must be the T4th law. But even before that, a lot of things happened. There was Boltzmann was a student, and Boltzmann used his data. So you are not telling me something wrong. So he used thermodynamics to prove that after all his teacher was correct. And we will go through that derivation just for your own interest sake. We will do that, how Boltzmann, by thermodynamics, he was able to say that heat transfer is any body in the world radiates heat according to its absolute temperature to the 4th power. Everybody, anybody in the universe, it emits radiation. It doesn't matter what temperature it is. It's just the characteristic of the radiation changes, but however, the total radiation from any body depends upon its absolute temperature, and the intensity of the radiation will be proportional to the 4th power of the absolute temperature. Okay, so I know to go through the theory a little bit. What is interesting is, let me just Max Planck, of course, there are 4 people who are really the pillars of radiation, naming Boltzmann, who really initiated this thinking, Boltzmann, I'm sorry, the experimentalist Joseph Stefan, Boltzmann, and then Max Planck, who really derived this radiation intensity equal to the Stefan Boltzmann constant multiplied by T to the power of 4. That Stefan Boltzmann constant is also distribution in frequency. It doesn't have the same intensity everywhere. It is distributed. That's Max Planck was able to derive that distribution behavior, and for that he got Nobel Prize. And there was another person called, even before this theory, Wien. He related this where exactly this distribution of this energy is related to that maximum the wavelength of that particular radiation multiplied by the absolute temperature of that body is a constant. He was able to prove that even before Max Planck's theory, so he got a Nobel Prize for that, Wien. So that's an interesting also. That is exactly explains the green gas effect. In other words, if you have carbon dioxide in your atmosphere, for the temperature of the sun is like 5800 Kelvin approximately. So the lambda is extremely small. So it's a high frequency is coming in, and it comes into the Earth, and Earth is typically like 27,300 degree Kelvin. So immediately it is a longer wavelength. So the carbon dioxide does not allow transmission; it traps it, and that is basically, in a nutshell, that is the green gas effect. So as you produce more carbon dioxide, it settles down in our atmosphere, and that really increases the temperature, and then polar melting and all sorts of bad stuff happens to the Earth. Okay, what is more interesting is the earlier. Let me just go to the next page. Yeah, I'm not going to go through. I hope Krishna has given you a copy of it, or if you don't have it, have her email to you guys, you can read it. But what is more interesting is, okay, there was in 1818, there was two scientists, Dulong and Petit from France. They said that the energy spectrum, energy emitted by radiation is proportional to mu, some constant, some other constant, a to the power of t. It fitted the data very well. It fitted at that time. So he was praised, and in fact he was gotten a lot of present and everything, Dulong and Petit. But then immediately you can find out there is an anomaly here. Can anybody say what is anomaly about this? It fitted the data up to some frequent temperature very well, actual data. You know what this problem in this particular data? At absolute temperature, there is no energy. In other words, at absolute temperature, all atoms all become quiet. Nothing can transmit. So this shows that there still be some transmission. So there is an anomaly. However much it explains it, it has a problem. So t is equal to 0, they have a problem. So even though, in fact, let me read this one interesting. They were given a plaque that seems to apply with considerable accuracy through a much wider range of temperature difference than that of Newton. So that was the plaque given to them, even though it was wrong. So you can imagine science really evolves through times of mistakes, and then innovation, mistake, innovation, and experiment. Without experiment, nothing can be done. So how did Joseph Stefan say that that it was proportional to t to the power of 4? What he did, he used the Petit's law experiment. He had a simple experiment in the conduction experiment. And he found out that the losses were considerable in that experimental setup. The conduction losses, because remember that I showed you the hemisphere. If those things losses are there on the side, you are not going to get an accurate results. So it has to be designed properly. But he did not want to build another new equipment. What he did, he estimated those conductive losses, and he accounted for it in the actual data. When he put the data back, sure enough, this became proportional to t to the power of 4. What is interesting is, I'll not show it to you. I don't know if you can see it in the presentation here. He has, okay, let me show you. So this is his equipment, conduction experiment here. Let me show it to you here. he shows the heat is equal to proportionally A T1 to the power of 4. He has the A. There's nothing but the Boltzmann constant, but he didn't estimate it at that time. He didn't know the law at that time, but he said that's equal to A T to the power of 4. So he did not do any experiment, but if you do it now from his experimental data, we can get that is 5.056 10 to the power of minus 8, even though it is really 5.67 approximately. 67 is very close, 669, but 10 to the power of minus 8. But remarkably, he was able to be very, very close with that kind of experiment in 1820s. So that's really fascinating. And then next comes in Boltzmann, and he was one of the proponent of atomic model, but his opposition by the Mach, the Mach number Mach, he was opposing him. So I think Boltzmann was brilliant. I would say even though he didn't get Nobel Prize, what happened is he killed himself. He committed suicide in Italy. But he was a very brilliant student and also a scientist and physicist. I don't know whether you in the statistical mechanics there is they call H theorem, and he proved that H theorem. So, but anyway, to make the story short, that Boltzmann was brilliant, and I will be. It's a very deceptively simple. He says that, and I will prove that in the next class because we don't have very much time to go through this. Basically, what he's doing is he is assuming the again. Remember, there was a dual model of the light. Light was either considered a wave or it's a bunch of particles. He says it's a bunch of particles. Let's say photon number of particles. Suppose it's in an area, enclosed area. It used the just Carnot cycle. The TDS is the heat transfer is equal to the change of volume. I mean change of energy, internal energy. That's equal to the energy per unit volume multiplied by the volume plus the work PDV. Then we'll go through this. What is the assumption is made is that the pressure that is inserted in the body of the cylinder is, remember each photon is traveling at light speed. So we can calculate that internal energy divided by 3 is the real pressure generated on the surface. So he adds that also. He says E over 3, and he just take the derivative with the internal energy is as a function of temperature. So he just does this, and then he calculates everything, and eventually what he gets is the d dt is 4E over t. Then you can solve the differential equation. You find that internal energy is proportional to the t to the power of 4. So we will do that next class. Let's do that. It's brilliant, and he made that that assumption, and then at least people started believing Stefan's assumption that the radiation energy is proportional to t to the power of 4. So then comes Vn, and Vn is able to get some other model for the distribution of that energy over the frequency. So he proposes some sort of a model based on exponential law and so on. So his distribution law, Vn distribution law says lambda t is a constant. In other words, any lambda at any t. So let's just go through that. I don't know whether the distribution is given here. Maybe I did not. Okay, so let me just go quickly. Okay, so before I what happened there? I'm sorry, this is not the correct one. Okay, so this is the radiation. Okay, so radiation, electromagnetic distribution. So let me just show it to you that before I don't want to belabor the point. So basically, at each temperature, the energy here, the energy on the y-axis is this is a spectral emissive power. In other words, at each frequency, what is the power emitted watt per meter square, and then the x-axis is like given in micron, per micron of the wave coming in. So lambda t is constant. So this is all one temperature. The lambda t is constant here. It's changing here. Lambda is changing. So this is the lambda t max. So I have everywhere where exactly you will get the maximum. And I can get the lambda t max is equal to 2.898. You take the derivative. We'll go through this derivation later on. But the important thing is this distribution of radiation energy, thermal energy, is distributed in frequency. For every temperature, is a unique curve can be drawn. So at 300 degree, this is the real Earth's temperature. But you look at the visual range is from 0.4 to 0.7 micron. This is our optical range. So we cannot see something glowing. However, if it is glowing around 800 degree, we start seeing something red, like a flame, blue flame, and so on. You'll start seeing. Remember, this is the 800 Kelvin curve. So this is the band of the visual. So this is violet to the red. So we can see approximately, if a flame gets about 800 degree, we can see the red. Okay, so that, and then blue is a little bit higher temperature, with between maybe 900 to 1000 degrees. So if you see a blue flame in your burner, that burner is around 1000 degrees. So anyway, Wien he didn't know this distribution. He just said lambda t is a constant, and that was also brilliant. Again, it is small steps and science improves in a small way. So that's very critical. So we will, for at least from a pedagogical point of view, I would like to derive how Max Planck was able to, this is Max Planck's picture. It looks like a crazy guy. He published his paper on quantum of action, and then 1900, around the time, he was able to really solve this. There was a problem when you do what exactly that the theory was. How did they come up with? So black body radiation. Suppose you have a body. If it is a black body, in other words, all the radiation that's coming in, it's getting absorbed. That's what the black body is. And a black body radiation is sigma t to the power of 4. So depending upon its temperature, it emits a radiation equal to this. Okay, suppose that radiation falls on it, it completely gets trapped. So the theory was, let's say there is a small hole and traps it, so it traps back and forth, eventually gets trapped. So the size of that, the geometry of this thing is that the size approximately is equal to the radiations coming in, lambda over 2. In other words, if I have a, let's say if I have a cylinder, there is a radiation coming into the wave. So let's say it's going like this. So size is exactly, so this is lambda over 2. So this to this is lambda. So this is lambda over 2. So it's an equal multiple of lambda over 2. Then it's back and forth. It goes back what's called standing wave pattern. So the premise was, if I have my length of that geometry should be equal to some numerical multiplication of the lambda over 2 of the scale. So how many such particles in the incoming radiation exist? I count those particles, attach an energy kT, and see whether I can find out the energy spectrum. That is how the theory developed. The people earlier, they worked on it, and they had a problem with it, because at high frequency, this energy spectrum was going up to infinity. So it was called ultraviolet catastrophe. It was famously called, if you go and Google it, ultraviolet catastrophe. We will do the next class. So what happened at a high frequency, energy blows up. So he had to, so Max Planck, instead of attaching energy h nu, discrete energy for each particle, h is the Boltzmann's constant, nu is the frequency, you get an average energy. And the average energy using Boltzmann's distribution, and you get the average energy using his distribution, you will find out if you use that average energy, it will not blow up. And you get exactly, believe it or not, you do all this approximation, you will be able to get sigma by calculations. It's unbelievable. Calculation is very close to actual measurement. Very, very close to. With all this theory, approximation and everything, it comes very, very close. So, and Max Planck won a Nobel Prize. So we would like to see that. It's in some of the physics textbooks, but we will just go through that next class. And I also go through Boltzmann's theory. Are there any questions today? Any questions? So I'm going to close the stop recording.